Hi friends, in the previous video we saw about the molecules which were not having a lone pair of electrons. We are dealing with the VSEPR theory. We are going to see how the shape of those molecules can be obtained. Okay, there are basically four types. Okay, if there are three lone electron pairs, then we have different geometry. Then if we have 4, 5 and 6, okay, so these are the types. So first let us see if there are electron pairs are 3 in number. If there are 3 electron pairs, then what will be the geometry? See, if there are 3 electron pairs, then either there are two possibilities. Okay, there may be two bonded pairs, bonding pairs electron, and one lone pair. So let us see what is the geometry of this structure if the structure has 3 electron pairs. Okay, so let here be the central atom, then let this be the electron pair, and this be one atom, and this be the other. So I have two bonding pair and one lone pair. So example for this kind of molecules is sulfur dioxide. So we can give example as sulfur dioxide. Sulfur dioxide, the Lewis structure, the sulfur dioxide has in this form. So sulfur will donate. See the electronic configuration of sulfur. It has 16 electrons. Okay, 16 electrons. The neon will be the inert configuration. Then we have 3s2, 3p4. So it will be like this: 2 electrons, and we have 1, 2, 3, and the 4th electron. So I have 6 valence electrons. In 6 valence electrons, 1, 2, 1, 2, 3, 4. I have already filled 4 electrons. I am left with one lone pair. So that will be the lone pair present here. So this can form the octet structure also. So this will be the octet for oxygen. Again, this is the octet for the oxygen because it has got 8 electrons. And for sulfur, 1, 2, 3, 4, 5, 6, 7, 8. So this will be the octet structure for sulfur. And these two remains as a lone pair. Since the sulfur and oxygen are bonded by 4 electrons, so it will be consisting of 2 bonds. So this will be sulfur with as a central atom. Then there will be 2 bonds between oxygen and sulfur. Again there will be 2 bonds, and the 2 electrons will form the lone pair. The bond angle is 119.5. So you can see that it is not linear, it is bent. So you can say it as a bent structure. So if you look at this structure, it is trigonal planar. This is the I have wrote this using the arrangement of electrons. So here is one atom. Imagine if it is an atom, then these are 3 atoms, then it forms trigonal planar. But the geometry of this structure is bent. So when we are talking about geometry, we don't consider the lone pair, we just consider the bonded pairs. Hence this is one atom, this is one bond, and this is another bond. So it is a bit bent, so we call it as bent structure. So this is the first type where we see if the electron pairs are 3 in number. Now let us move to the structures which are having 4 electron pairs. Okay, so if the electron pairs are 4 in number, there will be 2 possibilities. Okay, there are 2 possibilities. Either there may be 3 bonded pair and 1 lone pair, or 2 bonded pairs and 2 lone pair. Now first we will go with the 3 bonded pairs and 1 lone pair. So let us see the structure, how it goes. So let this be the central atom. Let this be the lone pair of electrons. 1 bond, 2 bond, and 3 bond. So this will be the atoms. So if you look at this structure, I said according to the electronic arrangement, it looks tetrahedral, like 1, 2, 3, 4. If you just join these bonds, you're going to observe that it forms tetrahedral structure. But now if we just draw the geometry of this, example of this type of molecule is ammonia. Okay, so let us draw the structure. This is the one hydrogen, this is the second hydrogen, this is the third hydrogen, and this will be the lone pair of electrons present. Okay, just join this. You're gonna see that there is a trigonal planar structure below, like it forms a trigonal planar structure. This is a planar. Above that I have a nitrogen. I have nitrogen above these three hydrogen atoms forming a plane. So it forms a pyramid, like this is the plane, then this is the nitrogen. It forms a pyramid like structure. So we can write it as the geometry as trigonal pyramid. Trigonal pyramidal. So this will be the molecular structure or geometry of this type of electronic pairs which are having four in number and which are having 3 bonded pairs and 1 lone pair. So this is the structure. General formula is A, number of central atom, B is the number of atoms bonded, so there are 3 number, and the number of electron lone pairs is denoted as E. So this is the general form of this kind of structures. So now let us move to the structures which are having 2 bonded pairs and 2 lone pairs. Bonded pairs are 2 in number, and again lone pairs are also 2. Let us see that structure now. Let this be the central atom, let this be one lone pair, let this be the inner lone pair, should be the atoms. So if you just look at the structure, electronic arrangement, you see it is again a tetrahedral. 1, 2, 3, like this. You just observe that it's a tetrahedral, 3 faces at the top and 1 below face. So that will form a tetrahedral structure. This is according to the electronic arrangement. But now let us move to the geometry. How will be the geometry of this kind of structures? So the general formula is A, central atom, number of atoms linked to this central atom are 2 in number, so B2. There are 2 electron pairs, so E2. So this is the general formula. So now let us look at the molecular structure. So for example, I can give for this type of compounds, it is water. So water is an example for this kind of molecules. So let me take oxygen in the middle, and this will be the one hydrogen, this will be the second hydrogen. I have 2 lone pair of electrons on oxygen. So the bond angle is 104.5 degree. So due to the presence of lone pair of electrons on oxygen, the lone pair of electrons required more space. Hence, for this requirement, these bonded pairs are made to move away from these lone pairs. So we know that order of repulsion is lone pair, greater than lone pair, greater than bond pair. So lone pair repulsion is more. So these two will try to repel from each other. Once they try to move away from each other, then there will be a repulsion between these two atoms, a bonded pair and lone pair. We see here. Due to this repulsion, again the hydrogen is made to move ahead. Here also we see the same type of interaction. Okay. So once we see those 2 types of interactions, one is here and the other is on either sides of this molecule, we see that the hydrogen atoms are made to move away from these lone pairs. Hence, we form a bent structure. So again we form a bent structure. So bent structure is called as the molecular geometry of a water molecule. This is the water. Okay. So this is the general configuration. These are the number of bond pairs and lone pairs. This is the example for this type of molecules, and the molecular geometry is bent shape. Okay, I have done everything using the order of repulsion. So friends, now let us move to the molecules which are having 5 electron pairs. So electron pairs should be 5 in number. There are again 2 possibilities. either there may be 4 bonding pairs and 1 lone pair. Bonding pair may be 4 in number and a lone pair may be 1 in number, or I have bonding pair to be 3 and lone pair to be 2. So let us look at the first case now. See, if there are 4 bonding pairs and 1 lone pair, then what will be the structure? So I have to place the lone pair in such a direction that there will be least repulsion. How can I do that? Let me draw the central atom. Let me draw equilateral triangle. And let me place a lone pair at one corner of this equilateral triangle. And let me place 2 bonding atoms at other 2 corners of this equilateral triangle. Now you can see that these 2 are far away from each other. Again the same thing. So this repulsion is least. I said that bond pair repulsion is the least. Okay. So I have made the lone pair far away from this bonding pair so that there will be least repulsion and the molecule becomes highly stable. Now I have already placed 2 bonding pairs at 2 corners of this equilateral triangle and 1 lone pair. So let me accommodate 2 more bonding pairs. That is 2 more atoms. Okay. So let me just draw one more axial plane, axial line, one more. So there will be the another B atom. So the another B atom. So you can see that these are going to make an angle of 90 degree with this plane, and these are going to make 120 degree. So they are highly separated, hence there will be least repulsion. Okay. So this you can just observe that it looks in this manner. Okay. This is one B atom, this is second, this is the third, and this is the fourth, and I have lone pair here. So you see that it looks somewhat a seesaw shape, like in a childhood you used to play like this. Okay, so this would be the fulcrum, and here there would be a seat so that the children can sit, and one person used to sit here and other here. So once this person put the pressure or force, then this would go up, and when he puts the pressure down, then this side goes up. So they used to play. Okay, so this is called as seesaw. So you can see that there is a fulcrum formed, and these are the 2 seats. So if I just twist this molecule in this direction for your convenience, so it looks somewhat like this. Okay, what I have done, I just shifted the molecule in this direction. So you see, it looks like a seesaw shape. It's a fulcrum and there are the 2 seats. So it will look like seesaw shape. So that's the reason the shape, the molecular geometry is given as seesaw shape. Okay. So example is SF4, sulfur tetrafluoride. So how I am going to get one lone pair is, sulfur is having 16 electrons. So neon, then 3s2, 3p4, 2 electrons in s orbit, then having 1, 2, 3 and 4. So among these 6 electrons, 2, 4, 5, 6, 4 are going for bonding. 1, 2, 3, 4 gone, right? There is one lone pair of electrons left, so we write one lone pair. So if I draw the structure, it looks in this fashion. So this is the sulfur central atom, and let me just draw a lone pair here. This is the fluorine atom. This is the another axial fluorine atom. So I need to draw 2 equatorial atoms. So this is the seesaw shape of sulfur tetrafluoride. So this is the example for bonding pairs 4 and lone pair is 1. The first one you already saw. The bonded pairs are 4 in number and lone pair is 1. So let us go with the second one, that is bond pairs are 3 and lone pairs are 2 in number. So now let us see what is the molecular geometry. Okay, let us see what is the molecular geometry. So this is the central atom as usual. Now I need to accommodate 2 lone pairs and 3 bond pairs. Now I have to think in such a manner that the lone pairs are kept at a far distance from each other. Okay, so let me keep at 2 corners of the equilateral triangle that we have considered initially. Let me consider the same kind of triangle, and let me keep the both the lone pairs at each corners, at the two corners of that equilateral triangle. Okay, so let me just draw that equilateral triangle here, and let me keep one lone pair, and this is the other lone pair. So this will be the one atom. Now I need to accommodate still two atoms. I have already done one, so I need to go with two. So let me just keep it above the plane and below the plane. That would be the better option. So this is one and this is two. So this is one kind of structure. So you can see a T shape. Probably you may not look it as T shape now, but let me just interchange the molecules so that you can easily understand. So let this be the A atom, and let this be the B, and this be the B, and let me just make B here, and let these two lone pair come here. So you can see now this is a T shape. This is these both are one and the same, but since it is on 2D structure, you may not be able to find out that it is a T shape. But now we can easily see that there is a T shape. So here it forms 90 degree. Here also it forms 90 degree. There is a formation of 90 degree. But due to it is a 2D board, so you may not be able to clearly distinguish that it is a T shape. Okay. So this is a 90 degree, and again there is a 90 degree here. And these molecules are 120 degree. So these are at the highest separation. These two lone pairs are highest separation. So there will be least repulsion between them, and the molecule becomes highly stable. So what is the reason for keeping these lone pairs away from each other? So let me consider a situation or a case in classroom that if two boys are fighting with each other, then what the teacher does, she tries to keep them away from each other. Okay, she will make the boys to sit at two different corners. If one boy is made to sit here, then the other is made to sit here. So teacher tries to make them sit apart from each other as much as possible. Okay, so if these two come close together, they will start fighting. Once they start fighting, there will be again disturbance in the class, and the other students will get disturbed in a similar manner. So teacher wants stability in this classroom. So she wants silence, peace in this classroom. So what she does, she tries to keep these students away from each other. In a similar manner, I am going to keep these lone pair of electrons, away from each other, so that there will be stability in the molecule. If these two come close to each other, there will be repulsion. If there is repulsion, you're going to see that there will be increase in the energy of the molecule. If there is increase in the energy of the molecule stability gradually decreases. So we need the stability of the atom. Henceforth, we keep these lone pairs far as much as possible. Okay. So example for this type of molecules is ClF3. This is ClF3. Why? Chlorine has two lone pair electrons. How? Chlorine is having 17 electrons, so it's a neon. Then 3s2, 3p5. 2 electrons here. Then 1, 2, 3, 4, 5. So I needed 3 electrons, right? These 3 electrons are done. I am left with 1 and 2. There are 2 lone pairs. So 2 lone pairs are present here in chlorine. So we can form this kind of structure. So the shape, if you look at the shape, it is T shape. You can see that alphabet, English alphabet T. So this is the central atom, this is. So using ClF3, how can we draw? And then this will be the Cl, then this will be fluorine, and this will be another fluorine atom. These are the axial, and I have 2 lone pairs, so they will be coming here. This is how you can draw the chlorine structure. So you can draw it in this way also. So these are the lone pair of electrons, so this can be drawn in this way. So this is the structure of ClF3, and it is T shape. So friends, so the last type of molecule remains those molecules which are having 6 electron pairs. Okay, the electron pairs are 6 in number. If there are 6 electron pairs, then there will be 2 possibilities. Either there are 5 bonding pairs and 1 lone pair, like 5 bonding pairs, and lone pair will be 1 in number, or bonding pairs are 4 and lone pair is 2. So let us look at the first case. If there are 5 bonding pairs and 1 lone pair, now we need to decide where to place the lone pair. So at what point can we place the lone pairs in order to get the minimum repulsion? So where can I fit it? So if I place it at the one corner of equilateral triangle, I will get 2 atoms at other 2 equilateral triangles, and 1 above and 1 below. But I have 5, so I will get only 4 atoms there. So where shall I put that lone pair of electrons? That will be something which is need to be discussed now. So where shall we put it? Any guessings? Any idea? So let us see if we can put at the top. I mean, if we can place the lone pair at the above the plane of the paper. Let us see that. Let us check. So let us consider a square rather than considering a triangle. Let us consider the different shape. Let us consider a square and see if we can settle with our requirements. So let this be the A, the central atom. Let this be the one atom, B is the second atom, C with the third atom, and this is the fourth atom. Now I have one atom and one lone pair. Where shall I put it? So let me just keep one bond here, and let me just keep a lone pair here. So I'm done. So these 4 atoms are far away and it forms 90 degree. So obviously it causes less repulsion. Okay. So this structure is called as square pyramidal. Square pyramidal. This is square and I have pyramid structure. So example for this is BRF5, bromine pentafluoride. So let us see that. Let us take bromine here, and let me draw a square planar. Square planar meaning, so imagine this is a square planar. It is on a single plane, so it is planar and it is square. So I have placed one atom here and the atom here, third, and this is the fourth. So I have placed 4 atoms, and B be the 4 atoms. I'm sorry, I should have written it as fluorine because we are taking fluorine, bromine pentafluoride. So these are the 4 fluorine atoms. Now I will place one atom as perpendicular to the plane. So these bonds are called as equatorial bonds, and the bond which is perpendicular to this plane is called as axial bonds. Okay, so let me place one bond above this plane. Okay, this is the 5th bond. So those requirements of 5 bonds are over. 1, 2, 3, 4, 5. So I need one lone pair. So what I will do, I will just place it below the plane. So it looks like this. So what I have drawn there is, it is exactly below. The lone pair is exactly below this planar. So this is the lone pair. So this is the plane. These fluorine atoms are on the 4 corners. Okay, and one is above the plane and one lone pair is below the plane. So this is how it looks. So we call it as square planar and have an atom above. So we can just draw a pyramid over it. It looks like a pyramid, like Egyptian mummy pyramid. So it is square pyramid. So the geometry of this structure is square pyramid. Okay, this is the structure for having molecules having 5 bonded pair and 1 lone pair. So let us look at the last structure, which is having 4 bonded pairs and 2 lone pairs. So this is the last. So 4 plus 2, 6. Okay. Now I have to accommodate 2 lone pairs in such a direction and in such a way that there will be least repulsion. So where shall I put it? So I did a square planar structure and I brought one molecule, one atom above the plane. Now where shall I, there I was having only single lone pair. Now I have 2 lone pairs. So where shall I put it? That is a point of question. Where shall I put it? Let me just try to put the lone pair above and below the plane. Isn't it? So that would be a better idea. So let me draw a central atom and let me just place these atoms on the same plane, and let me just place these lone pairs above and below the plane. So that would be a better idea, I think, because these lone pairs are far apart from each other, so there will be no reason of repulsion, there's no chance of repulsion, and this will be forming 90 degrees. So again there will be a vast difference between these bonded pairs and the lone pairs, hence the repulsion will be less and the molecule will be stable. So for example, so this kind of structures are called as square planar. When we are dealing with the structure, when we are writing the geometry, of any molecule, I said you, we should never consider these lone pairs. We should just consider the bonded pairs. So there are 4 bonded pairs which are on the same plane. So I can say square planar. So square planar, they are on the same plane. Square planar, and above it I have one lone pair, and below it I have a lone pair. So these are the 2 lone pairs. Okay, these are 2 lone pairs, and I have 4 I can say atoms at the 4 corners of this square planar, and I have 2 lone pairs and above and below the plane of this paper or book. So example for this kind of structure is xenon tetrafluoride. So this is a good example. So let me tell you how I wrote xenon fluoride. See the electronic configuration. So number of electrons in xenon is 54, right? So how I remembered is, let me just write the halogen atoms. It's helium, neon, argon, then I have krypton, and I have xenon. This is 2, 10, 18, 36, 54. This is how the halogens come. So if it is 54, the previous element will be, the previous group period will be having krypton. So let me just write krypton. So the helium comes under the first period, second period, third period, fourth period, and this is the fifth. Okay, so I can write 5s2, 4d10, 5p6. So this is how you can write the electronic configuration automatically. Okay. So the easy trick is just see in which period it comes. So it comes, this is the, it will be in the first period, helium, this is the second, this is the third, this is the fourth, this is the fifth. So whatever the period number is there, the same will be with S and same will be with the P. So you can just notice that. And D will be 1 less. When it comes to the P, F orbital, there will be 2 less, but that time it will be 6s and so on. It will be like that. So this is the trick you can just see. This is the electronic configuration D10. So let us neglect this D orbital because it has nothing to do with the valence shell. So I am going to consider just S and P. So there are 2 and 6. There are 8 electrons, right? 8 electrons. So it will be orbital diagram will be somewhat like this. So I need 4 bonded pair of electrons. 1, 2, 3, 4. Done. I have 2 lone pairs still. 2 lone pairs. So I am going to use this. And these lone pairs will be above and below the plane. And 4 bonded pairs will be at the corners of the square planar. This is how we can write. So xenon structure will be xenon square planar structure. And these lone pairs will be above and below the plane. So this is the xenon tetrafluoride. Xenon tetrafluoride, and this is the structure square planar. So this is the geometry of those molecules which are having boron, the bonded pair are 4 and lone pair are 2. So the general formula is central atom A, B is 4 bonded pairs and lone pair are 2. So this is the general formula. So let me just write all the general formulas in single row so that you can easily remember things. So if there are 3 bonded pairs, if there are 3 electron pairs, then it is A, B, 2, and so it is 2 bonded pairs and 1 lone pair. If there are 4 electron pairs, then there are 3 bonded pairs and 1 lone pair. I can write it in this way: A, B, 3 and E, 1. Okay. And if there are 2 bonded pairs and 2 lone pairs, then I can write A, B, 2, E, 2. If there are 5 electron pairs, then there are 4 bonded pairs and 1 lone pair. So structure, the general formula will be AB4 E1. You can write or you may not write. So it's your choice. If there are 3 bonded pairs and 2 lone pairs, you can write AB3 E2. If there are 6 electron pairs, then there are 5 bonded pairs and 1 lone pair. So it will be AB5 E. If there are 4 bonded pairs and 2 lone pairs, then it will be AB4 E2. So this is how you can write the general formula for 3 electron pairs, 4 electron pairs, 5 electron pairs and 6 electron pairs. So this is how we can determine the geometry of the molecules using VSEPR theory, and these are the molecules which are having lone pair of electrons. I hope you have understood the concept. If you have any doubts, you may just comment it below in the comment box. Thank you for watching. Have a nice day.